Okay, third lecture today, linear data structures. So far, we have seen algorithms, an introduction, and we have seen also analysis of algorithms and different techniques. So that's what we have seen so far. In this lecture, we are going to talk about the data structures because we have not talked about data structures yet. Okay, so when you write a computer program, it's a set of instructions, or an algorithm is a set of steps, a sequence of steps. I hear my voice back. I hear my echo. Can you make the microphone off or something? Mute it. Okay. So when you write a program is a set of is a sequence of instructions, and in these instructions you are going to handle or process some data. So, for example, you define a variable, you write to the variable, and I still hear my voice, which is very annoying. Okay, can you mute the microphone at your side? Is it possible? Say it again. Yeah, I'm saying I am hearing my voice.
Okay, we can switch off our microphone. So you, from your side, stop the volume.
Okay, let me try that. But then I will not know when you ask a question anyway. So just scream if you have a question. So when you write programs, you define variables and use these variables, and these variables you are going to organize them in what we call a data structure. So sometimes you define arrays in order to store all sorts of variables you need. You have a program that is going to find the maximum of some numbers. You are going to put these numbers inside an array, and then you loop through the array trying to find the maximum. Okay? So we have algorithms, which are the instructions which are defined by the instructions in our program, and we have the data that we deal with. Okay, so algorithms and data. So today we are going to look at some data, very very simple data structures, but which are very important in your case as computer scientists or programmers. This is a very important sentence here. It says that an algorithm can be very efficient, but the efficiency of the algorithm assumes that the data is structured in a certain way. So as you will see later on in the course, we will see that data, if we organize it as trees, for example, we can derive very efficient algorithms for searching this data. So if we put data inside an array, we end up, for example, taking a linear time in order to find something, in order to find an item. If we put the data in a tree, we take only logarithmic time in order to find something, in order to find an item. If we put the data in a tree, we take only logarithmic time in order to find the item. And searching is one of the operations that crop up a lot in your life as programmers. A programmer, you will always need to deal with data, search for certain item, etc. So depending on data structure, your search technique or your search algorithm can either be efficient or not. So the choice of data structure is going to also affect the efficiency of the algorithm. So before starting to talk about linear data structures, let's just refresh our minds with how things look in main memory. So when you write a program in source code and then you compile it in object code, so your program is going to two different parts of the memory. One is the space for instructions, and one is the space for data. So here we are talking about the space for data, which is very similar to the space instructions. So what we have, basically this is main memory, this rectangle, open-ended rectangle is main memory. These here are addresses in main memory. They're not always 2000, etc. This is just an example. And these are here what we call the cells of main memory. So if you have a variable x, it is stored in a cell here. Another variable is stored in another cell. At the object code level, when you say something like load variable x from memory location, something like that, what you're saying is basically look at the address 2000 in main memory and give me whatever is inside that address. Okay, so main memory is some addressable space. The cells are next to each other, they have addresses, and they store data. And in order to get a data from main memory, we give it the CPU, not you. The CPU sends the address to main memory, and main memory gives it back whatever is stored inside that address, or in the cell which is indexed by that address. Okay, so that's just a refresher of what main memory, how it looks like, because it has a relationship with the array data structure, which is the first data structure we are going to learn. So we all know what an array looks like that. We usually draw it horizontally. So an array has indexes, which are these numbers here on the top. And arrays can be indexed from 0 to, for example, n-1, or from 1 to n, if the size of the array is n. So again, these are called indices or indexes, depending if you speak British or American English. And these here are just your the data, cells and nodes. We call them cells or we call them nodes. Okay, so we store data inside an array, and each location is indexed by some array, by some index. This array here is, sorry. So as you can see, the array, this address becomes this one, this address becomes this one, this address becomes this address becomes this one, this address becomes this one, this address becomes this one, etc. And the content inside memory, this becomes that one, this becomes this one, and 5 is that, etc. So in other words, an array is just a piece of main memory. Okay? An array is just a piece of, when we say an array, we mean that there is a piece of main memory in which we are storing all the elements. If 10 is next to 1 here, okay, the first cell contains the variable or the value 10, and the second cell contains the value 1, and the third cell contains the value 5. In main memory, it's going to be 10, and then 1, and then 5. So if two pieces of data are adjacent to each other, which means they are next to each other exactly, in the array, they are also going to be next to each other inside main memory. So this is why we also call the array a contiguous data structure. A contiguous data structure. This is a G. Okay, because elements are in continuously one after the other, and the same continuity here is reflected in main memory. So the other thing that we all know about the array is that all the elements inside the array have the same type. This is not very important for us because we are not really interested in that, but it's worth mentioning. For us, all we want to know is how the array, the structure in the array is going to, or how when we perform different algorithms to do all sorts of operations on the array, how efficient these operations are going to be, etc. So this remark here is just a programming observation, right? It has nothing to do with efficiency. So this is the array. Okay. Now, there is another thing about the array. The array has what we call start address. So the first element in the array has a specific address in main memory. In this case, it's 2000. Okay. Now, why is that important to mention? That's because the address of we say that the address of the first element of the array is we call it S. Okay, S, for example, is 2000. In other cases, it might be different. Okay, this is the address of the first element. Now, if we want the address of the second element, all we have to do is to add the index of the second element. For example, what does that say? So the address of A of 2 is going to be equal to 2000, for example, 2000 plus 2. Okay, I 2 2, and that's going to be 2002. Okay, so basically all we are saying, in order to find the second element or from the array, all we need to do is to add 2 to the start address of the element, or from the array, all we need to do is to add 2 to the start address of the array in order to get us 2002. And from there, we know that this element is the second element in the array. Okay, so if we want to say x equals A of 2 in your Java code or any high programming language code, what does that mean? When the program is compiled and it's object code and it's inside memory, what does that mean? All it does mean is that we already know the address of the start of the array, 2000, and we just add 2 to it and get 2002, and then the CPU tells the memory, give me the data which is stored at the address 2002, and memory says, here you go, take it. Okay, so this is how we address something in main memory and the relationship with the array. Now all this blah blah blah, this is all to say that in order to get an element or to access an element from an array, we need constant time. And the reason is, so when we want to say x, when we said x equals x plus 1, we said this is a constant operation. We said that's constant because we are using assignment, we are using addition, and we know these things take a constant amount of time. This is using just a normal adder, if you know about adders, and this is just loading values from register to register of main memory to CPU register. It's very simple. It's big O of 1. However, now what we are saying, we are talking about an operation, for example, x equals x plus A of 1. And we want to know if this operation here, or this statement here, is it actually big O of 1 or is it not? Now we know about this and we know about this, but how about that? Maybe in order to find the element at index 1 in the array, maybe it's not constant time. Maybe there are lots of things happening. So we don't know. And that's why we actually went and explained that. We explained that in order to find element at index 1 in the array, all we need to do is to know the address of the array, and we already know that, and we add to it the index of this, the index of the element. So in order to find A of 1, we just add S to 1 and then find what is A of S plus 1. That's what we are saying in this slide here. Okay, so in order to find, to get a value a of 1, for example, okay, this will take us actually just, we need to make a simple mathematical addition here, okay? Addition, which is just a simple mathematical operation. And we know that this is very simple and it's big O of 1. So in order to find an element from the array, or to fetch or access an element in the array, it's a big O of 1 operation. So now we can say that if we have a statement like x equals y plus a of 1, we know this addition is big O of 1, and we know array access is big O of 1, and so everything is big O of 1. So all this just to say, if you see a statement in your code saying a, where a is code, saying a, where a is an array, a of something, a of I, then we know that this is big O of 1. So we can use this as a rule. So from now on, array access is big O of 1. And now you should know how to explain, if you get the question, why array access is big O of 1. If you know the answer now, you have understood this slide. Now, records are just like arrays, okay? They are also contiguous data structures. So when you define a record with a first name, with an age, and with a gender, what happens is all this data is copied into adjacent cells in main memory. So this is a record which has a name, an age, and gender, and we have created two instances of this record. Record, object in Ada, class in Ada, structure in C. These are all the words for the same programming construct. Okay, so this is a record. You are designing software for a supermarket, and the supermarket deals with products and customers, sells products to customers. So as a designer of this software, you are going to use something called the customer class, where you basically create a record for customers, age, gender, purchase history. We're talking about sites, for example, like Amazon. You always need to create an account, and etc. So you create a record for customers, and also you create a record for products, like a book. So you have a book, you have the price, the title, year publication, how many people bought that book, etc. So records are very useful, and for us, we already know what records are, but maybe we don't know that when we store them in main memory, they also take adjacent places. So if you have a record of 100 elements, and you want to access the element which is number 100, that is going to take you big O of 1. So you have a record, it has 100 element, 1, 2, 3, blah, 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 until 100, and you want to access this 100 element here. In order to access that element, it's going to take you big O of 1, constant time, because it's just like the array. In order to find the address of this element, all we have to do is to add 100 to the start address of the record. Okay? So arrays, records, are contiguous data structures which have big O of 1 access time. In order to access the first element of the array, so you have an array of 1,000,000 items, and it looks something like that. Starts, for example, at 1, and it finishes at 1,000,000. If we say A of 1, we are going to take a constant time. If we say A of 10 to the 6, we are also going to take constant time, because to get here, all we have to do is to add start address plus 1,000,000. And the same applies for a record. If for any weird reason you have a record which has 1,000,000 items in it, and you want to access the last item, or let's say the item here 10 to the 5, all you have to do is to add the start address of the record to 10 to the 5, and you will get a resulting address, and then you just have to access this address from main memory. So both are the same in the sense that in order to compute the exact address of the element we want to access, all we have to do is a simple mathematical addition. Right? So as a summary, arrays and records are contiguous data structures. So elements are adjacent in main memory. Advantages of using arrays or records is that we have a constant time access time. Okay, this one here is going to be obvious later on. We don't know about pointers yet. And finally, if we have some cache memory, then the array is going to be useful for us. Now, why is that the case? Just very, very briefly. If we have... Oh. So, let's say that this is main memory. And X, and it has the data X, X and Y stored like this, and we have our program which says Z equals X, and then Z equals X plus Y. So this is our program, and it is executing in CPU. Right? Now CPU, let's say that Z is already in one of the registers of the CPU. So Z is here, and we want to perform these two operations. Now the CPU wants to say, well, I'm going to execute Z equals X. Now, how I'm going to do that? Where is X anyway? So the CPU is going to talk to main memory and say, please give me X. So CPU go all the way here and tells memory, give me X. Memory says, okay, here X. CPU execute that, and then CPU wants to execute this. Oh, I have X. I brought X from this execution now. It's inside the register, inside me, so I can use it just from here very quickly. Now I need Y. How do I get that? I need to go back to main memory. I need to get that and come back. Now the difference between the CPU getting a variable from the register and getting it from main memory is basically like using a Formula 1 car and using a donkey. Okay? It's that much difference. Okay? So it's very fast for the CPU to get data from register compared to main memory. Now this is if you don't have a cache. Now what happens if you have a cache? When you have a cache, yes, so you have a cache here. So what happens in this case? That's cache. We still don't have X. We have, that's cache. We still don't have X. We have Z. Now we want to get X. So how do we do it? So the CPU wants to execute that statement. It doesn't find X. So what it does, it goes to the cache. Do you have X? The cache says no. So we go to main memory. Okay? Okay? Now main memory gives X to the cache. However, it does not just give X. It gives a whole piece of data. The size of this piece is going to depend on the size of your computer bus, which we are not going to talk about, but it gives a whole piece of data. Right? So it's going to, now it says, the cache gets X, but memory is generous. It gives it all this data. So it gives it X, and it gives it Y as well. And everything here as well, which we don't care about. Now CPU gets, so the data is copied to cache and then to CPU. Now we have X here. And then CPU execute this instruction, and then oops, I need Y. Now we go back to the cache. Ta-da! Y is already here. So we bring Y just from the cache. Now, if the path here takes 100 cycles, this could take just 2 cycles. Now, that's very fast. Now, this is why cache is important. Now we can see that if we have a loop, if we have an array, let's say from 1 to 4, and here we have A of 1. We said the array is a contiguous data structure. We will have A of 2 here in main memory, A of 3 here, and A of 4 here, and the loop which is going to access the array is somewhere here. Basically, it's going through all the values of the array and computing their sum, for example. So the first time we don't find A of 1, we are going to get it from the cache. We don't find it, we get it from main memory. Main memory gives us A of 1 and A of 2 and A of 3 and A of 4 because they are all together. Okay, so it puts them in the cache. Next time, when we want to find A of 2, we just get it from the cache. And when we want to get A of 3, we get it from the cache. Because this data is close to each other in main memory, when we fetch the first one in the cache, we also get all the other ones for free. So next time, we don't have to go all the way to main memory in this very long journey. We just stop at the cache and get it from there. So the first one will be a cache miss because we don't find it. And after that, these are all going to be cache hits. Now, what do you get from all this discussion? We're not really interested in the architecture. We are interested in the fact that arrays, when they are in main, because they are contiguous, when we reference the first element of the array, it is going to be brought into the cache in addition to the other elements in this array. And this, how many other elements are brought in the cache, this is defined by the cache size. Okay, actually it's called the cache block size. So lesson is, because arrays records are contiguous, they are very efficient when we have a cache. Okay, I don't know if you've done some computer architecture or not, but you did? Right, okay. So that's either something old or something new, but the lesson from it is what I said. Because the data structures are contiguous, then what? Then if you have a cache in the system, you are going to benefit from this contiguity. If you have a cache in the system, you are going to benefit from this contiguity property. Right. So far we have seen data structures, arrays, and records, and we have seen that they have constant access times. Now, what kind of problems do we have? The problems which are not related to efficiency really is that arrays are non-flexible. So if I want, I need to know how many elements are going to be in the array. Okay, for example, I write a program that is going to ask the user to input 20 numbers, and I ask the user, okay, go ahead, input 20 numbers for me to process, 20 integers, and the user is going to give me 20 integers, and I will store them inside the array. Done. Now, let's say I want to ask the user to input some numbers, and I want to return the average of these numbers. I don't know beforehand how many numbers the user is going to input to me. So I cannot really use an array because an array is fixed. And this kind of array is called a static array. Okay, it's fixed. I need to know how many elements I am going to store. When I define it, I define this array has size 100. It cannot contain more than that, but maybe the user is going to input more than that. The other kind of array is called dynamic. This is not supported by all programming languages. It's basically an array which grows in size with time. Okay, so some implementations starts with, like in Java, starts with one cell, and when you add another cell in main memory is created dynamically. And then you add another value to the array, another cell is created in the array dynamically. This data structure is called array list in Java. It's very efficient. In other implementation, in other programming languages, you might find that an array has size 1. If you add some data to it, it becomes times 2. If you add further data, another element, it becomes size 4, and starts each time starts doubling in size. Okay, so these are different techniques for implementing dynamic arrays. So, but for our course, what we are talking about here is really efficiency. So these two things are not related to efficiency. They are just some extra knowledge. But in terms of efficiency, let's talk about doing some nice operations in the array. Let's say that we want to insert an element in the array. So we have an array. Okay. And we want to make some insertion. 1, 2. So this is array 1, 2, 3, 4, 5. And we want to put an element right here. We want to put an element in the middle. So how do we do that? If you were programming that, if I tell you I want to put the number 10 inside, I want to insert it here. How would you do that? Okay. Okay. What if we want to insert? We don't want to update. Okay. We want to insert. Updating means we are going to change this number to 10. Okay. Let me draw it in a better way. So we have an array. It has the elements 1, 2, 3, 4. This is supposed to be 3, 4, 5. And we want to insert here. We want to insert this index 1, index 2, index 3, index 4, index 5. We want to insert the number 6. If we said we want to update the value, we are going to put 6 here, delete 3 and put 6. When we want to insert, we have to make some room for it. So in this case, we are going to do some shifting, right? So what happens? 1, 2, 3, 4, 5, 6, 7, 6, 7. So we shift whatever is here to here, and we shift this to here, and we shift this to here. So we end up doing what? 5 goes here, 4 goes here, 3 goes here, and now this one is empty. So we can put 6 here, and then we have the 1 and 2, they stay where they were originally. So we do shifting. So we need to make space for the new number, and that's why we have to shift everybody in this order so that nothing overwrites another thing. Okay. So we do some shifting in order to insert an element. Now, obviously, shifting can go very wrong. For example, let's say I have an array of 100 values, and let's say 60 values are full, and I want to insert in the first cell. So how many shift operations do I need to do? So this is the size of the array. This is the number of cells which are full. So there are 4 empty cells, and I want to insert the number or the element. I want to insert it in the first cell. How many shifting operations do I need? I need 60. Every one of these must move. Every one of these must move. Okay, so there are 60 of them. All 60 of them must move to the right. And in order to say it again.
The last value on the right. Where is low?
What?
The last value.
The last value?
Yes, the last row in red.
Yeah.
Has not. When you make a fix, so the last value, what happens for the top? Like if we go for the right, the last input, where it's go? The value of the last input, where it's go?
Okay. If you see what I have drawn so far, I said these are elements which are full, and these are